Okay, good evening and welcome. Thanks for joining us at UW Space Place tonight. It's the second Tuesday of the month, so we have our guest speaker tonight, as always. The guest speaker tonight is Jonathan Rebelski, who is a third-year grad student in analytical chemistry here at UW-Madison. And he's working on some interesting research in the Whitacus-Weaver group on campus. He'll tell us more about that. But as you'll see in the talk, Jonathan has a strong background in music, which he acquired as an undergrad at Grinnell College, where he was a joint music and chemistry major. So he's bringing these two things together for us, and how, well, as we'll see, harmonies and things relate to the universe more widely. So join me in welcoming Jonathan Rebelski tonight.
Hi, thanks to everyone who came in person or who's tuning in either now live or in the future virtually. I do really cool, interesting research with the Whitacus-Weaver group here at UW-Madison. I'm not going to be talking about that tonight, though. Instead, I'll be talking about something else I find really interesting. The Musica Universalis, understanding the small and large-scale motions underlying the universe. So as a very brief introduction to this talk, before we get to the actual introduction, you'll notice there's bubbles at the top with names of the different sections. If you feel like this presentation is dragging on forever, you can see where the light at the end of the tunnel is. We also have a slide counter at the bottom for similar reasons. So in a lot of today's science, and especially outside of science in today's culture, there's this idea that most things we see are these individual, unique, discrete systems. And that's a very modern idea. If we look back through the ages, most of the time what we see is people believed systems were linked. And so, especially astronomy, was seeing all of these stars, all of the things we see at the night sky, they must be linked together somehow, and they should be somehow influencing us. So we're going to talk a little bit about that today. We're going to talk about what does harmony mean outside of this universal context, and then we'll sort of talk about where we see these same concepts pop up in other sciences. So that's the order. I guess I might have given a slightly different order. You'll notice all of this harmony is, all of the harmony in astronomy is very Western focused. For better and for worse, modern astronomy draws its roots primarily from the Western tradition. So that's where we're focusing, because that's how we can trace a line of thought. There's other fascinating stuff that happens in astronomy historically around the world, and I would really encourage everyone to look at that. The same is true in music. We're only really looking at Greek music leading to Western music. We're not going to look at any of the other fascinating ways we can do harmony outside of the Western tradition. So with that out of the way, what is the universal music? So this universal music is an idea that stars and planets we see moving across the sky, they're moving together. They're bound by natural laws to move in harmony. And that means a lot of different things to a lot of different people, but the key word that I'm focusing on here is harmony. So what is harmony? Harmony is the relationship between different periodic motions, and in particular, harmony is going to refer here to this assignment of meaning, right? Just because we see two things moving in cyclic patterns doesn't mean we see them as linked, and just because things are linked doesn't mean we will see them that way. And so it's this assignment of meaning that really gives rise to the concept of harmony. It's much more common historically for you to just see two linked things and go, they must be linked. But we're sort of seeing that now again, which is also great. So where do we see harmony? Harmony shows up in oscillating systems that are linked. In modern usages, we tend to think of this as happening at the same time. So if I play like an E on a piano and a G on a piano, that would be harmony. But if we look back at ancient thought, especially in the Greek world, harmony also referred to the list of possible sounds that you could produce. So all of the notes on a guitar, for instance, would be the harmony of the guitar, even though you can't play all of those notes at once. So how do we describe it? We're going to use some math and some visual descriptors based on what felt easiest for me as I was writing these slides. So an easy thing we can start with is just the sine wave. Here, if we imagine the y position of this dot as the sign of a function t, as we change t, we can see how this dot moves up and down and up and down. If we take it one level of abstraction, we can get rid of the sine wave and just have this moving dot. Dot's moving, nothing too horribly exciting. If we then plot an x position of cosine of t, and we plot these two together, we end up seeing that you form a circle. If you have, as the red dot, has the Y position for the blue dot and the X position of the yellow dot, you can see it moves in a circle. And that's really interesting if you care about the unison, which is the most simple harmony. It's two notes played at the same ratio. As we look forward, we'll start to see other kinds of harmony that we can get. Most of the way that we think of harmony today in the sciences and in music is with the harmonic series. So the harmonic series, you might see mathematically represented as the inverse of this, so 1 over 1 plus 1 over 2 plus 1 over 3. Here we're using 1, 2, and 3. That's because you can take durations and frequencies, invert them, and you end up with those same relationships. You'll notice, maybe, that instead of just having n times f for your nth harmonic, we have to add 1. That's just a conventional thing. Your base frequency is your base frequency, known as the fundamental, not the first harmonic. Your first harmonic is double your first frequency. So what are some examples that aren't just the simple case of a unison? So we can see here a 2-to-1 ratio, a 3-to-2 ratio, and a 9-to-8 ratio, where those refer to how quickly the yellow and blue dots are moving relative to each other. One thing you might notice is that the bigger the numbers get, the more of the space it seems like they occupy. And that's true. This is also something you can sort of hear. So if we look at this 1-to-2 ratio, you should be able to hear that it sounds, if we ignore the overall tone quality, it almost only sounds like there's one note playing, right? But if we then look at the 3-to-2 ratio, we can start to hear the second note come out. It still very much sounds nice and hopefully pleasing to your ears. But if we get to the 9-8, by this point we've sort of gotten close enough that the two notes are going to start colliding a lot in our ears. And it doesn't, it sounds a kind of pretty. You'll see these notes, a 9-8 ratio very often in modern music. But it's a little more rubbing against each other in the ears. So you might expect that this goes on forever, right? If we have like 1,000,000 to 1,000,001 ratio, it should sound horrible. But our ears are only so good. And so after a certain level, you'll just hear it as one note again, even if they are varying ever so slightly. And that's something really important to think about here, is that we have harmony, which we can describe using beautiful mathematical relationships, and we have harmony as it exists in the real world. And those are not the same. We'll talk future parts in this talk about how mathematical underpinnings of reality and math are different, but for now we'll move on. So what's harmony in music? When I say harmony, I think most people will probably assume I'm talking about music. And that makes sense. That's generally the way we conceive of it today. So we can think of harmony as I mentioned before, the simultaneous sound. Like we play multiple notes on a piano, we can think of the harmony there in that chord. Or we can think of it as what notes are allowed. Right? There's only 88 keys on a piano. The harmony of the piano, you could say, is only those 88 notes. In that sense, we talk about the piano's temperament. So what is a temperament? Temperament refers to how the notes you are allowed are chosen, both how many you're allowed and how they relate to each other. We can think about like a very simple case. What if we have one note, and that note's at 200 hertz? We can still make something resembling music with it, right? We can play with dynamics, we can play with duration. It doesn't sound completely unintentional, but it also doesn't sound fantastic. Even Mary Had a Little Lamb has 4 notes. Most pop songs you'll hear today have at least 7 notes. And so we have to think, how many notes do we want in our scale? Obviously we want more notes, right? More notes is more freedom. But at the same time, you don't want 2 notes that sound so similar that you can't tell them apart, because then you'll end up with this compositional problem where one composer will choose note A, one composer will choose note B. They'll sound basically the same, and so you end up more or less with the illusion of choice. Historically, in Western society, we've chosen 12 notes as our perfect number. And as we can see, there's the minimum error for your scale comes at 12 notes until you get up to 41 notes per division. There have been people, especially since the 20th century, building different instruments and tunings. They use all sorts of different numbers of notes. We won't really be talking about them here, but I would welcome any questions about that afterwards. So at this point, you might be asking, what do I mean by relative error? So we should talk about the tuning systems. Most Western tuning systems are built to satisfy, hopefully, 2 criteria at a minimum. Octaves are in tune, and fifths are in tune. Ideally, every other interval is also in tune, but as we'll see, even just these 2 requirements make it so you cannot build a scale. Why? In short, mathematics is to blame. To be more specific though, right now I've sort of used frequency and math words to talk about math concepts, and music words to talk about music concepts. That may not immediately click for you as being the same thing. So very briefly, here are some of the most common intervals you'll see in Western music, along with their frequency ratio in 5 limit just intonation. That's just the technical disclaimer I'm putting here for anyone who might be really pedantic and want to complain about my claiming that a minor third is a 6-to-5 ratio. So a common rule of thumb is the smaller the numbers are, the nicer the 2 notes sound together. Right? We heard in the octave, it basically sounded like 1 note, and we heard in that major second that you could very clearly hear you were playing 2 notes, and they didn't necessarily agree with each other. So why can't we build a scale? Well, if we look just as a way of scales can be built by stacking these intervals. To make a nice scale, we want it to repeat at the octave. There's lots of historical and cultural reasons for that, but at the end of the day, we just decide we want our octave to be here, and we want to stack fifths. So, what ratio of 3 over 2, the second, third, fourth, will equal some power of 2. Those of you who have more math experience than me might immediately see that there's no way to solve this problem unless n and m both equal 0. Those of you who don't necessarily see that right away, if you think about it, there's no 2 in the numerator, and so there's no way for us to ever get to a power of 2 up top. And so in such a way, we end up with this problem where if we stack fifths and have nice in-tune fifths, we can never end back up at the note we started with, even if we divide by 2 to get to octaves. So how do we deal with that? There's sort of 4 major schools of thought in Western music. The first one is the most ancient one. It was developed by Pythagoras. He says, we just won't use one of these intervals. We'll call it the wolf fifth because it sounds like a fifth. It sounds like wolves howling. A few centuries later, we go Pythagorean tuning. Also doesn't really give us good thirds or seconds or let us use all of the notes we want. And so we'll take a couple of intervals, we'll break up this bad interval, make a couple of intervals kind of bad, but say most of the intervals will still be pretty good. With mean tone tuning, you end up with this really interesting effect where different keys have different sounds because the ratios are off ever so slightly differently. Bach's well-tempered clavier, for instance, is an example of this mean tone tuning where not only do the notes sound different because they're in different points on your keyboard, but the ratios between them are different, and so you end up hearing different sounds, which is really interesting. Of course, we then throw all that out when we get towards the Romantic period, and we move to what the most common thing is today, which is known as equal temperament. In equal temperament, we say octaves are important. Great. Other than that, I want every key to sound exactly the same, which is nice, right? Like if you're a singer who wants to sing a song you like, but it's a half step too high, you can just transpose it down and it sounds identical. The downside is this means each half step, because again we have 12 half steps in an octave, so we have 12 divisions in an octave, each division then becomes the 12th root of 2. And so you don't end up with any of these nice, pretty mathematical relationships. I can't have the fun little moving images of the 3 to 2 ratio. And then we can go even further. And pianists and piano builders found that if you made your octaves a little too small at the bass end and a little too big at the upper end, it actually sounds a little bit nicer. And so you end up with stretched octave equal temperament, where none of your intervals are in tune with each other. And that's sort of where we've ended up today. Of course, there are people trying all sorts of different things, and sometimes they sound good, sometimes they sound really bad, sometimes they just sound interesting. But rather than just having me tell you that these fifths don't sound good, I thought I could play a couple of examples. So this is, again, just like the nice, perfect, just-tuned fifth, a 3 to 2 ratio. Sounds nice and clean. We then move down to the Pythagorean tuning. This is called a wolf fifth. I don't know if you'll agree with that. It still sounds like wolves baying to me. Right, it does not sound nice and harmonious as though we've got 2 well-tuned instruments together. Mean tone tuning, again, sounds sort of close. Sounds in many respects a little bit better tuned than just, which gets back to that psychoacoustic effect that just because 2 notes are mathematically in tune doesn't mean we'll hear them as in tune. And then, of course, equal temperament. This should be the fifth we're mostly familiar with. If you listen really carefully, you might hear the 2 notes start to phase with each other. That is because the notes are constructively and destructively interfering with each other in a way that doesn't happen with just intonation. So So now that we've talked about harmony in music, we can talk about where harmony shows up in astronomy. And, of course, it makes sense, to me at least, to start with modern astronomy. That's what we use. That's what we know to be true for whatever variations of true we're willing to accept in science. So the easiest example is the Titus Bode Law. The Titus Bode Law states that if you have multiple planets in a solar system, you should expect to see their orbits about double the distance apart each time. In musical terms, these planets are octaves apart each time. Of course, future research shows that number is really 1.728, not 2. That's closer to a 9 to 16 to 9 ratio, I think, which is a very different interval. But we still see this idea that these planets are somehow linked in how they're orbiting with each other. We also see Kirkwood Gaps, especially in our solar system. So what this is if you plot where we see asteroids as a function of distance, integer ratios of how quickly they'd orbit compared to Jupiter, we see these gaps where there's no asteroids. But the prevailing theory for this is that these gaps in the asteroid belt are caused by Jupiter's force exerting and destabilizing orbits in these different ratios. It's a really fascinating idea. It's really interesting. It does sort of provoke this thought of, where else would these harmonies show up? The other example we still see is in Jupiter. Again, Io, Europa, and Ganymede orbit at a 1 to 2 to 4 ratio. So every time that Io orbits, Europa has half an orbit and Ganymede has a quarter of an orbit. And it's theorized that these orbits are actually stabilizing each other because of their relative influences. We also believe that Pluto and Neptune have a 2 to 3 ratio, which helps keep both their orbits a little more stable. So now that we've talked about where we see harmony, even today, where we've sort of given up on this idea that the universe is singing to us, I think it's kind of cool to talk about historical. So we can start with Babylonia, as I think most Western science does. So the Babylonians used arithmetic for their models. For them, the goal was less, why is the universe like this, and more so, how can we have a regular calendar system, at least based on the records we still have. And so they would use their math, and they would predict things, and they'd say, cool, prediction verifies experiment, we can move on. Very similar to the way that we think of modern scientific inquiry. Sort of the most important thing that they've given us is this conception of the year. So, we talked about how harmony refers to assignment of meaning between different cyclic systems. And if we kind of think about it, there's no reason that the rotation of the Earth, the rotation of the moon, or orbit of the moon, and our orbit around the sun should be linked quantities, right? They're just 3 movements throughout space. And yet we really do want them to be linked, right? Because it feels nice that a day and a year have some correspondence to each other, or a lunar month and a day have some correspondence with each other. And so they found that 19 solar years is approximately 235 lunar months. We can also break 235 down into this slightly smaller expression, which is cool, right? It shows that we have 19 years of 12 months, and in seven of those years, we get an extra month. And so as a result, you can start to say, cool, 100 years from now, what month will it be at this point? And you can do that, and that's great. So then we move forward into the Greeks. And so the Greeks, rather than focusing on this concept of we can measure this and predict this and model this so well, most of the Greek astronomy that we have is more philosophical. It says this is how reality is, not how we see reality. And so models are not tested based on, do we have like 0.01% accuracy? It's does this model and does reality, are they the same? And they used geometry more than algebra. So they referenced shapes and the motion of shapes. So we start, as all things do, with Pythagoras. Pythagoras is known for a lot of math. He created the first scale, which we talked about earlier, where we stack fifths. It's said that he was led to develop this tuning system by walking by a forge one day. He heard hammers hammering on different anvils. And he was shocked that despite how, it doesn't matter how hard you hit an anvil, it always sounds at the same tone, and different anvils have different tones. He later linked this to this concept of harmony. He also was one of the first in Western thought to show that the Earth is a sphere, but that proof is lost to time. Later recollections of what he did suggest that it was something about how when we have lunar eclipses, the shadow is circular. I'm not an expert in that, so I would advise you to read those sources. So after Pythagoras, we move on to Plato. So Plato is really where we get sort of the biggest philosophical underpinning for this universal music. So Plato thought of everything in the universe as sort of macrocosms and microcosms of each other. So we see reflections of ourselves in the stars and the stars in ourselves. And so he truly believed that we had these planets as music, that the motion of the planets is some grand song and symphony. He generally said it was because it's moving so slowly that we can't hear an oscillation that lasts one full year, which makes sense. Others then later posit that it's rather than it being too slow to hear, it's that this music is so all-encompassing and so universal that we just don't hear it because it's so constant we tune it out, which is sort of a sad concept if we think about it. So from Plato, we move on to Pliny the Elder. As a brief aside, Pliny the Elder is generally credited as creating the first encyclopedia. So rather than writing, this is what I've done, he said, here's what a bunch of other people studied and found, and that's really cool and really useful, and one of the last surviving things we have from Pythagoras. And it's very tempting, we can look at the ancient Greeks and go, they had this geocentric worldview, they must not have known anything. Or they have these harmonic models of the universe that don't make any sense. What were they thinking? But even with the math they had and the very limited tools, they still have really good predictions for different things, right? The orbit of the Earth around the Sun, or the Sun around the Earth in their view, and the rotation of the Moon are accurate to within 2 decimal places. Their length of an eclipse cycle is exactly what we have to this day. Other measurements are, of course, less accurate. And so I think it's important to note here that just because we have different conceptions for how the universe works than the ancient Greeks did, it's not necessarily a value judgment on our data is better so our models are better. It is partially that. But it's also a fundamental way that we view the world differently than them. They went into their problems assuming that the universe must be linked, and so they saw these links. We go into the world assuming the universe is a bunch of independent bodies, and so we see independent bodies. And so to end the sort of ancient world, Pliny writes about this relationship between the heavenly bodies that's ascribed to Pythagoras and creating a scale. Of course, even he notes that this scale is more of a refinement more entertaining than convincing, right? It's a nice story, even they weren't sure it was true. But they said, oh, the notes between the planet, like the distance between the planets and their ratios and how they orbit, can be expressed as a scale. And so if we assume that we're using just intonation for each interval, we can listen to what the scale of the universe sounds like. So we've got the Earth at 200 hertz, which hopefully you can hear. And then we've got the Moon a step above that, so at a 9-to-8 ratio. And then Mercury is a half step above that. Doesn't sound super lovely. Venus is another half step up. Again, clashes a little bit. The Sun, they thought, was so far away, it must be a whole minor third apart, which does sound kind of nice, right? You're back to harmony that we're familiar with as Westerners. Then we have another step to Mars. Kind of sounds, warlike, joyous, if we're going to start ascribing meaning. Half step to Jupiter. Another half step to Saturn. And another half step to the rest of the stars, the zodiac. Because even back then, they had this concept that, yes, we've got all these things orbiting the Earth, or as we now know, the Sun. But the first 7 bodies must be different than these stars that we see in the night sky, like Polaris or the constellations, which we, again, affirm. Another thing you might note about the scale we've constructed here, it doesn't sound a lot like a Western scale, right? A normal Western scale has slightly fewer notes than this, and the notes that we have are broken apart differently. That has a lot to do with the way ancient Greeks constructed scales, which is very different than how we do it today. Again, that's a little too much of an aside for this talk, but I would love to talk about it afterwards if anyone has questions. So then we've moved past the ancient world. The next 1,000 or so years, we have developments, but none of them have sustained us to this day, and so we can ignore them. We move to Copernicus. Copernicus is generally famous for the heliocentric worldview. Since the ancient Greeks, people had posited the heliocentric worldview, but it was always dismissed. His was the one that stuck, and so he gets to go down in history. He did also have this idea that these planets that are now, we know, rotating all around the sun, there must be some sort of a harmony linking how they move. He didn't have the math or the observations to nail down what that relationship was. But that leads us to sort of the last hurrah for this idea of this universal music, Johannes Kepler. So Kepler, as we know, came up with the 3 laws of planetary motion, was very instrumental in sort of modern astronomy as we know it. He was also from his early days, he was convinced that the planets orbiting the sun must be orbiting, as the Greeks thought, with some sort of relationship to the Platonic solids. Some of his ideas lasted a really long time, right? He posited that there has to be another planet between Mars and Jupiter, an idea that lasted a really long time until now we know there's the asteroid belt. He also predicted Planet 9, which is still predicted, posited to different levels of credulity depending on who you talk to. As he kept going in his career, though, he realized the Platonic solids don't accurately explain reality. Right, Platonic solids, as he saw them, required circular orbits, which, as we know, we don't have. We have elliptical orbits. And so what he later theorized was that it was still elliptical orbits, but it was these orbits had some sort of a harmonious motion to them. Of course, we now know, to some extent, that's not true, right? The planets more or less orbit independently of each other because of how overwhelming the gravity of the sun is. So now we've talked about sort of a historical look back at astronomy. We can look about ways that harmony is used in other sciences today. There's the really low-hanging fruit here of simple harmonic oscillators. So those of you who've taken an introductory physics course might be familiar with this concept. More or less, it's you have a weight on a spring that you've displaced, and if you track the motion of that object over time in a frictionless surface that doesn't emit any energy, you see that you have a sine wave that forms, and as you have different weights and different springs, you can end up with the whole harmonic series. Those of you who've taken quantum mechanics might see where we're going next. The particle in a box is sort of the quantum mechanical version of the simple harmonic oscillator. So what separates quantum mechanics from classical mechanics and sort of reality as we know it is I can occupy any space from here to there pretty much continuously in classical mechanics. In quantum mechanics, I can only occupy certain specific values. And as it turns out, the energy that a particle has in this quantum system is an integer multiple of some base energy. So you end up seeing the harmonic series again and other harmonic relationships. An interesting thing to note is that, especially in chemistry, you'll see these sort of reference to vibrational modes of a molecule. And you'll very quickly hear that the vibrational modes diverge and are anharmonic. Similarly, when you're playing a string on a guitar or any other stringed instrument, or playing an instrument that has harmonics otherwise, such as a wind instrument, we have this expectation for where the different harmonics should lie, and we have the math to prove that's why it is. But because we have these physical instruments, not a perfect string of infinite length and zero width, the upper harmonics start to diverge from the actual harmonic values that math would predict. And so that's part of what gives different instruments different tones. You can also see this taken to the extreme in a bell. So if you've ever heard a bell, you might notice that it sounds like it rings, right? It gets louder and quieter and louder and quieter, even once you ring it once. And that's because the overtone series in the bell is nowhere near the harmonic series. And so the different oscillations clash and cancel with each other in such a way that you end up hearing constructive and destructive interference. All this to say, again, we have the world of math where we have beautiful number relationships for harmonics, and we have our world here where we have not that. And finally, this is new research. As with all new research, may or may not be supported in the future, but recent work suggested that biological systems have themselves a harmonic system with overtone relationships. So not only do we see these like 12 and 24-hour cycles, but these 12 and 24-hour cycles have a cycle again at 48 hours and 96 hours, and so on and so forth, which is really fascinating because no one had really conceptualized that in biology as far as I'm aware. Of course, if you are a biologist and know otherwise, I would love to hear that. So the way that they did this analysis is using something called a Fourier transform, which is really fundamental to science, music, math, a lot of things. So what is a Fourier transform? So Joseph Fourier proved that we can describe any function as a sum of sine waves if we give them different frequencies and amplitudes. So the physical sciences rely on this. It's fundamental to interferometry and radio astronomy. In chemistry, most spectra of molecules, so if we shine light on a molecule, we can know a lot about the molecule based on where it absorbs the light. We hate doing it wavelength by wavelength because that takes forever. If we have a frequency transform device, we can shine light really quickly, change its frequencies, and then do some magical math and end up with a nice picture of frequencies. And in music, it's really great because you can stop, you can record a voice or record a trumpet and say, I know, it should be like a C, but what other notes does the trumpet make that make it sound so different from a piano? And you can take it and take your thing in time space and move it to frequency space. So say, oh, it's got C, it's got its first harmonic at a G, but it's ever so slightly sharp. And that way, they're all sort of fused. So as a quick example of how Fourier transforms work to end this talk, square waves are really common in, if you think about like a circuit, right? We can have a circuit that's either on or off, that we'd want to go at some regular pattern, so we'd want a square wave. But of course, all we have to work with is sine waves in Fourier's world. So how do we build a square wave out of sine waves? Well, the equation is the summation from 0 to infinity of sine of 2 pi times your base frequency times 2n plus 1 with an amplitude of the inverse of 2n plus 1. So each successive sine wave gets faster and smaller. And we can watch that build, right? So what do the sine waves look like? Here we've got our base sine wave, the n equals 0 case. Then we add the first harmonic, second, third, and fourth. I did say second harmonic. That's a little misleading. Square waves are really famous in the musical world because they only use odd harmonics, right? We see this 2n plus 1 value. So if we were doing actual harmonic analysis, we would say, the second harmonic and fourth harmonic. But we're not, so we'll say first, second, and third. And you might be looking at this picture right now and going, well, that's really pretty, but does it actually, resemble a square wave when you add it all together? And the answer is yes. So, at n equals 1, we see a sine wave. We had our first secondary sine wave, and we can see it's starting to look somewhat square, but still nowhere near good. We had another one, and it's starting, we're getting there. We still got these annoying bumps. 4, I would call this close enough at this point. 5, again, depending on what you need. If all you need is vaguely high and vaguely low, right? If your sensors can't pick up the difference between these waves, 5 waves alone can get you to a square wave. But then we can go to 10, 100, and 1,000. And of course, right, if we zoomed in on any of these waves, we'd see that there's still a little bit of oscillation. But physical systems don't have perfect resolution. And so, to some extent, it doesn't matter what math would tell us it looks like. What matters is that to our eyes and to the approximation that I built when I coded this, it is a perfect square wave. Wish I had a lovely little concluding slide here to talk to you about how isn't this wonderful, but I don't. So thank you for listening. I'd be happy to take any questions.